is a continuous space. How do you do error control in a continuous space? It's a lot more complicated. The thing with the error operator, you can discretize. And that's the second biggest insight after. You can discretize your set of error operator. And after that comes the direct connection to mathematics. They form a group. Okay, so they are a group. We can use abstract algebra. Well, there should be some symmetry in that group. Can we characterize the group? What happens if that group acts on something, right? What will that be? In abstract algebra, what will that be? A group acting on a set. What will that cause? Come on. I will retract your undergraduate degree if you cannot answer that. A group acting on a set, what will happen? You can look at what? At the orbits. Right? You can look at the orbits. So that's why we can use mathematics to help our colleagues in physics doing this. So that's the progression of ideas. If you get that, I'm happy. You don't need to get the details. You get that progression of ideas, you can read most works in quantum information, quantum error control code. Okay? Things start to get a bit clearer? Alright. So, you can express non-trivial error acting on a qubit as Pauli matrices. These are 2 by 2 Pauli matrices acting on a qubit. Okay? Fantastic. I have a set of basic operators. Now I can play with them. So we have sigma x, sigma z, and sigma y, which is a combination of sigma x and sigma z. I here is the square root of -1. So I have this, and I can characterize it. Now, what happens if the error operator acts on a qubit? So sigma x is a bit flip. It flips the probability. Remember that the state is characterized by the basis elements multiplied by a complex number that will give you, when you take the modulus squared, the probability that when you measure, the state collapses to that basic state. Okay? So what happened here? Sigma x is a bit flip error. It simply flipped the probability. Sigma c is a phase flip error. It flips the angular measure. Okay? And sigma y is a combination error. You know that here, earlier you see it's a combination error. You have sigma z, you have sigma x, and then after that you multiply by I. You add the I, the complex square root of -1. Is that clear? Now, again, state. You can think of it as vector. The operator you can think of as matrix. So we are in business. We can characterize how these operators play together. We can write them in terms of group. We can look at the orbit. We can look at the characters, you know. All the tools that you learned from abstract algebra over these years turn out to be useful after all. Okay? So, sorry. Alright, so you can play around with this if you want later, and then here is the relation. Sigma x, sigma y, sigma z, order 2. If there is a bit flip happening there, how do you correct it? Apply another bit flip. Right? Remember, it's just changing the probability. So now you swap the probability again, it goes back to the previous one. Finish. Same thing, you can check the properties of the others, and sigma x and sigma z anti-commute. Very nice relationship. Okay, so quantum error operator. You can characterize the error operator in the following way. I raised to lambda for lambda between 0 to 3. And this W here is a basic non-trivial Pauli matrices plus the identity. Identity means there's nothing happened, no error, everything fine. Okay, so It is a C-linear unitary operator acting on a C to the n basis. Remember, in an n-qubit system, we have the basis. The basis we can express as strings, as binary strings. So everything is fine. We play here. We are in order. So what happens when an error acts on a state? We can split it by look at the effect of the error on every basis element. Because the state is a linear combination, you look at the effect of error on each basis element, you know how it acts on an arbitrary state. Very nice, right? So think of it that way. Now, we are not yet to group, okay? Still set. We haven't get into the group. So set of error operator. Here's a set of error operator. It's a finite, but non-abelian because of the anti-commutativity of sigma x and sigma z. Cannot be abelian. Its cardinality is this. So now what happens if I have two error operators and I take their product? Look, these are tensor products, okay? Because this error operator W1 act on qubit position 1, qubit position 2, qubit position n. So then, okay, you can check, can verify that the product of two operator will be this operator. Okay, now take out your ball pen and paper. I don't want you to sleep. Now you do this example. All of you, before I give you something even more difficult, okay? So, I just use n equal to 2, so this is a 2-qubit system. My first operator is nothing happened in the first one, and bit flip in the second, and E prime is this. Okay? Now you use the rule here to find out what the what E prime is. Okay? Like this. So you add the power. Okay, you add the power. So first, you express it this way. This is I raised to 0. This is also I raised to 0. Now you write it that way. What will you get? This one is just a product. Tensor the product of that. Tensor the product of that. Quite easy. Verify that you get this. And then now you change the order and see if you get that. Can you follow? Is it clear what you need to do? Okay, now I change. Oh, not yet done. Is this correct? Sometimes I deliberately make it wrong, just to make sure that you actually did it and caught me. Is that correct? Yes or no? First one is just this and that, so it's sigma z. This one and that, sigma x, sigma y. Remember here the order matters, okay? The order matters. Left first and right. So here identity times sigma z, that's sigma z. Here sigma x times sigma y, sigma x, sigma y. And after I simplify, remember sigma z is I, sigma x, sigma x, sigma. Okay, so there is this connection that sigma y is I, sigma x, sigma z, so then you can simplify that. I think that one is probably the one that makes you confused. Here. You have this anti-commutativity property. So, this one becomes that. Why is it that you want to express this product of two matrices into one, well, it's a lot simpler to write it into one. Like this one, I can express it that way. So, everyone okay with that? Happy? That's what you do with the error operators, okay? Now, let's continue. All of these are easy to verify. If you still remember your abstract algebra. So the center of that group is just this. So you mod out the I raised to lambda. Okay? Then everything else inside will commute. Now notice that E prime is plus minus 1 E prime E here. Why plus minus 1? Because that's the joint eigenvalue. It's either plus 1 or minus 1. Here you have F2, right? So it's just only these two values. Okay, so if I mod out the set of error operators, so I take the quotient group here, the set of error operator, take the quotient with the center, this will turn it into what? Into an abelian group. That's why we study the center of a group, right? You take the quotient of any group with its center, automatically it becomes abelian. So, we call it abelian two elementary group since we have this. So you look at an element here, it's always of order 2. And in fact, it is isomorphic to this, F2 to the n, under addition. And this is a giant step in the understanding of how to control quantum code, actually. So, a physics problem now completely translated into mathematical problems. Okay? So, two things can happen. We help each other, or the mathematician decides the problem is not interesting, make it even more general, get a lot more results, and send it back to the physicist, and the physicist says, I told you not to do that. I need the other direction. Don't go too much into that. Help me with the original problem, okay? And that's pretty much the story so far, unfortunately. So we're happy to get this. We generalize it to a very, very general thing, and then suddenly we end up with a system over F128, F1024, and then when you translate it back to the language of physics, what dimension are we again? Then, you know, conversation lost. Yeah, that's what happened a lot. So now, I'm going to introduce a new notation that makes our work simpler. I have an error operator. Look, this one, right? We have this isomorphism, right? So now let's, instead of writing it in the left-hand side here, let's write it in terms of this. So, I have an error operator. I'm writing it this way. I raised to lambda plus L, and then XA and ZB. Where A here, the vector A tabulate at which position there is a Z error. An X error. The vector B tabulate the position where the Z error happened. Remember, the sigma Y is a combination of X and Z. So essentially, you need to care about X and Z. Okay? It's a wonderful shift, actually, because then it will make it amendable to techniques from classical coding theory. You see here, write it this way. Again, you still have your pen and your paper, right? Okay. This example. So this side, you do E. You write E in that notation, okay? This side, you do E prime. You look at the operator already, you write them down already? Okay, so now, let's go there. Write it this way. Write it in terms of this vector A and this vector B. So A will take care where X happen, B will take care where Z happen. So tell me what happened. What is E? What is the representation of E? 0 and what? I forgot myself. Okay, so here nothing, no X happen, second one X happen. So it will be 0, 1. Okay, for the vector A. What about vector B? 0 and 0. Hey, don't be happy yet, it's just 2. Later I'll give you 10. Just make sure we know, I mean, how to read this table, okay? Is that clear? How you do it? Okay, I hope you remember. So this one. Remember when you take the mod out, when you mod it out, the center contains I raised to lambda, right? And at some point we will just throw it out. We just discard it. When we take the center, this part gets discarded. And now we are going to keep track of the error operator just by looking at the A and B vectors. So far clear? You happy? You know a little bit now how to handle error in terms of strings? Okay, so we have the strings. Now the advantages of the new notation, the respective actions now becomes just this. The set of operators that has the sigma x component, you just add them. If it has the z component, you just take -1 times the Euclidean inner product, and that's that. You can verify it easily actually. Okay, and then what happened? If I have two operators, I know how to check whether they commute or they anti-commute just by looking at the inner product here. It's just the inner product of the A vector, so the part that keeps track of the X component with the part that keeps track of the Z component of the other operator. It's like cross, okay? At this, A times B prime. B prime takes care of the Z component in E prime. Okay? It's like cross, like that. So, prove the statement later during the tutorial. No, I think you'll ignore me, you'll just go and enjoy sightseeing in Yogyakarta. But okay, later on if you're bored, not doing anything, do something like this. Okay? Just prove the statement, this statement. That to check whether they commute or anti-commute, you just now need to check this symplectic inner product. We call it symplectic inner product. Okay? That's symplectic inner product. So I have two of them. Okay? Remember, one represents one error operator, the other one another error operator in this language. And then you just take symplectic inner product. You can also write it in terms of the matrix form. And then of course, if it is a valid inner product, you can test it is a valid inner product. You can define the dual. Okay? So, a subgroup is abelian if and only if, you know, after you take out the center, so you consider the cosets, is a symplectic self-orthogonal subspace of this. Now it's completely group theoretical problem. And this is where we in the computer science and mathematics community started thinking, why if I remove this F2, I want FQ. The physicist says, dude, come on. I don't need FQ. I need F2. And maybe F3. But we produce a lot of paper on FQ. A lot of paper. And then after that, we throw in structure from rings. You know, a lot of structures from rings. put gray map on it. I'm guilty as well with that, okay? Many years ago I did that. But if you look at the original problems, you understand why many of our results are ignored by our colleagues in the physics department or in the physics community, because they say F64, sorry. No, I'm not saying that therefore it is not valuable, okay? I'm just saying that if you want to help them in the quest of controlling error in the quantum world, that's where you should concentrate. Now, of course, we like to play with mathematical structure, that's fine. You can play with that. But please don't ask our colleague to implement it, they don't know how to. Okay? So, here. Now what about the weight? Quantum weight, right? There's one component so far that I haven't discussed, which is the distance, and this is where it comes. Okay? It's a quantum weight. Quantum weight is basically the number of positions where something other than the identity happened. Something other than the identity operator happened. That's what this formal expression means. Okay? So, now this is interesting. If you take En delta is a set of all operators with quantum weight up to delta. So these are all operators where the identity operators happens in at least n minus delta places. The non-identity happen only in up to delta places. Okay? So that's the weight of the operators. Now, you have this identity that is basically come from something like the analog of the sphere packing. The analog of the sphere packing for classical code. We're just going to need that to prove the Hamming bound for quantum. Okay, so here is the Néel-Laflamme condition. This is the main criteria for quantum error correction. It was set up long ago by Manik-Néel and Ray-Laflamme. So here is the distinction between quantum and classical error. In classical error and code words are vectors over the same field. As I mentioned, in quantum world, you have operators, error operators, and states. They're different. So, a quantum code can correct up to L quantum errors if the following conditions are satisfied. If initially two states are distinguishable, distinguishable means the Hermitian inner product is 0, then after the respective error, so here E1 act on V1 and E2 act on V2, they are still distinguishable. Okay? So, that's the key. If I collect all of the error operators up to weight L, okay, and I take two error operators from that set, any two, if I start out with two distinguishable states, two distinguishable quantum states, after the errors act on them respectively, the changed state are still distinguishable. Originally distinguishable, take any two error operators, apply to them respectively, they are still distinguishable. So Q has minimum distance D if this product is 0 for all E in the set of all error operators up to weight D minus 1 for all distinguishable V1 and V2 in Q. Okay? That's the notion of minimum distance. Minimum distance means I take error operators with weight up to that minimum distance minus 1, I can still do a correction. So, the nice thing is that the parameters and correction capability, okay? This is triangle inequalities, nothing fancy. The second one is a quantum code with distance dq can correct up to L dq minus 1 over 2, analogous to the classical case. So a quantum code has three basic parameters: the length, the dimension, and the minimum distance dq. Look, the dimension here over c, okay? The dimension is over c. So we often use the notation on the left or on the right, similar to when we use the non-linear and the linear one, okay? But the thing is here, in the classical sense, if you don't use the square bracket, you use this bracket only, right? This is usually considered to be the size of the code, not the dimension, but here you used it as a dimension. So I'll skip the purity part. It's not going to be useful for today's discussion. If you want to look at it, you can go back to it. Why? Because we need to discuss weight enumerator there. There is no time to discuss weight enumerator. So we have analog like the bound, right? How good is a code performing? Then you need to get the bound, lower and upper, as usual. So if a code is pure with this distance, then you have this. Q is perfect if it meets the bound. Okay. Analogous to the classical case. Okay. We will just use this to verify something later. We'll go back to this formula. So here's the main flow of ideas that I'm not going to discuss, but the full discussion is in that simple lecture. I'm going to recap the flow of idea. The flow of idea is like this. We choose an abelian subgroup G of the group of quantum error operator En. Okay? This subgroup G, we associate it, look, I'm saying associated with, okay? I'm not saying you use the classical code. Associated with the classical code, which is self-orthogonal under the symplectic inner product. Okay? And G acts on the big space, partitioning it into a direct sum of chi here is a character, eigenspaces with chi a character, an additive character over the group G, okay? So the properties that our quantum code Q can be fixed to that Q related to that additive character follows from the properties of C and the dual under the symplectic inner product. I'm sure the number 3 and number 4 is unintelligible at the moment because the full discussion with the proof and everything is in that full set of lecture. But you can go back to this. That's the flow of idea. So what we call the quantum code is this, which is the partitioning of this big space. So when someone asks you, okay, so what is quantum code? How would you answer? We can use classical code for it. Yes, you can use it, but how? At least at the end of the day, you know how to explain that a little bit, at least to yourself. Okay, so let's go back to quantum code. Okay, I have the group. It is actually this group. Okay, and it is isomorphic to this group. Okay, so sigma x and sigma z are Hermitian unitary. Then X AJ and X BJ are also Hermitian matrices. The tensor product of Hermitian matrices is also Hermitian. Then you know that this is what happened if this is what happened to if you have elements GJ, you can express this in terms of the vectors A and B. The key is to express error operators in terms of strings, binary strings. Okay? And this is how the partitioning of the space happens. So that is this number 3, which is completely unintelligible at the moment. It's okay, it is there, if you want to revisit it later. And now we are now in the last part, from classical to quantum. And what I have explained to you so far is actually my reading of two things. One is this paper, which is an absolute must-read paper if you want to study stabilizer code. Okay? This is the work that connects quantum operators to the mathematical structure as geometry. This is not an easy work to read, but it has all the basics. Everything that people built on so far comes from here. You look at who these people are. You know, Peter Shaw, of course, don't need to explain. Eric Rains is the mathematician there. Neil Sloan, if you know online encyclopedia of integer sequence, that's Sloan, yes, that's Sloan. And the expert on lattices and so many different things, okay? So Sloan, I trust his book. Sometimes I didn't check the proof. It's a bad thing. And Bob Calderbang, any electrical engineers will know his name. So you see how interdisciplinary this thing is. I imagine there must be getting together, discussing this. Shaw has a background in physics and computer science, and these two are very strong mathematicians, and Calderbang knows a lot in the implementation side. And even them takes 2 or 3 years to formulate the whole thing. So there are... And the second source is a PhD thesis of Daniel Gottsman. That is a very important source as well. Okay, so what happened here? If C is k-dimensional self-orthogonal subspace with respect to this symplectic inner product, you define the dual with respect to that symplectic inner product. Okay? Now the distance is connected to the distance of element here. The dual minus the original code. Okay? If you have such a classical structure, this stabilizer code exists. Look at that statement. Statement is very precise. There exists such a code. Okay? It doesn't tell you, use this code, you get that code. No. This characterizes the error operators that you can work on and guarantee that such an encoding is possible. That's what it is saying. Okay? If the details are blurred to you, just think about it. There are some classical structures from which I know the property of the quantum code. Examples. You want more examples, more difficult than this? I can show you as well. I think I like more difficult one. Okay, so you go here from code tables, okay? From code tables you go to QECC, yeah? It's quantum error correcting codes. And then from there you will find what you need. So my example to you, actually I cheated when I prepared the lecture because I didn't actually compute all of them. I borrow from Marcus' thing. Okay, so what does it say? It says, I have a code. This code is actually perfect code. It satisfies the Hamming bound I showed you before. The proof is simple. You use the property to check that everything there is satisfied. Okay? So, this is optimal code. the progression of idea is Peter Shaw has a 913 in the ancient era of quantum computing. So it was his the first work that says it is possible to do quantum error control. And here is how to do it on a very small scale. That was his paper back in 97 or 94, I cannot remember exactly, but ancient time. Okay? He said use 913. And then Eric Rains come up with something else. I have 713. And then this one come actually only after they get into the stabilizer. Okay? After they formulate all this stabilizer, then they know that how to construct this. So this is 513. So it correct one error. It correct only one error actually. That's how miserable we are. We don't really have a very powerful error correction so far. So here, stabilizer matrix. Now I want you to do the following. Write the operators. Write these four operators. Okay, in terms of sigma x, sigma z, sigma y. So, the first one is keeping track of the x. The second one, keeping track of the z. Okay, so write me down the operators. What is this first operators and second operators and third operator and fourth operators? Come on, the first one. Who's done? First one is what? First position? Sigma? Sigma y. Both error happens. Both x. Okay, so this is how I usually do it. Look at this and this. Both happen. That means combination error. That means y. Nothing happened here, nothing happened. So identity. Nothing happened here is only z. Here and here only x. Here and here y. That's how you read it. Okay? Clear? Very simple, right? Once you have this, but finding this is not it's not always simple. So, what happened? Your error 1 is this. Y, I, 3 is z, 4 is x, 5 is your first error. Then you take 2, 3, and 4. The set of error operator that you can handle is all of these products. So it's a set generated by E1, E2, E3, E4. You know that there exists a quantum code that can handle these error operators everywhere here. Anyone done with the last row? What is the last row? I, Z, 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 Z. So if you read physics paper and you see they're writing here Z, X, I, Z, X. That's that in that language, in our language, okay? So don't get scared. What are these? It's quantum code, but I haven't seen this. That's basically it. Okay? So you can continue. You can look. You see, even at a very short length, there are room for improvement. You can improve if you want. There. It's a good exercise when you feel a bit depressed, you know. We feel unhappy, you know, heartbroken or something. You say, okay, I'm a bit bored. Let's construct the stabilizer, the error operators that we know exist here. As I said, the tables. This is for binary, okay? You see, there is a lot of space for improvement. In our recent ISIT work, we improve on, I think, 4 locations. 4 locations only, and that's already, you know, it's accepted to a very good conference. So only 4. If you can fill up a little bit here, especially on the big qubit, maybe 100 or 128, that will be nice. At least you will have your name listed there as construction provided by so and so. Okay, so it's much nicer to look at the example live on the tables, and that's what I'm doing. You can check, okay, that all those vectors there, if you look at it as binary vectors, they are symplectic. So that if you look at it as classical code, it is self-orthogonal under the symplectic inner product. I wanted to give that as a homework last time, but then thinking that probably too much to explain. Okay? So now, this was the main result. And then there are extras results. This is what happened. Okay, that was symplectic inner product, right? We in the coding theory community more used to the Euclidean inner product. That is our #1 inner product we use all the time. And then after that, because of this quantum code, the interest to go into Hermitian inner product. Trace Hermitian actually, because the code doesn't have to be linear, it can be additive. But that's another matter. So, can we use Euclidean dual containing code? Yes. You can. And actually, you use this and then you connect it to that main theorem again. So it's actually just special cases. Okay? So I write down here the rather complete proof, but then that's a statement. So sometimes you read papers in coding theory journal and it says it's quantum code, but then the construction comes from Euclidean dual containing code. This is the reason. By now it's already standard, so they don't usually explain it. They just say, I use this approach. Okay. And here is a very famous CSS. Is again Calderbang, Shaw, and this time Steen. Okay. Steen is actually a physicist. And, he first went to the libraries and then looked up for the theory of error correcting codes. And he plucked out the simplest one. He said, okay, I will choose a simple example because he's not an expert there. And he chose Reed-Muller code and a few other codes. And because he knows the construction for quantum code, he got good results. At least in those early days, it was good. So, Calderbang, Shaw, and Steen. Here you have a pair. You have a pair of code, okay, and they are nested. So actually you can think of it as C inside D, but then if you want to use the inner product, then you write it this way, okay? You take a code, and then you take the dual under the Euclidean inner product, and if it is inside another code, then you can use the CSS construction. Again, the proof is connecting it to that main theorem, and then so this is called the CSS construction. CSS is strictly inside stabilizer. So there are stabilizer codes that you cannot construct using CSS. That's a proof. And here is a Steen enlargement. Steen, as I said, learning this thing from scratch, learning classical codes from scratch. So he's probably the other direction from us. We start with classical code and go into quantum. Well, he did. He understands the quantum setup first and then try to pick up good classical codes. Okay, and he says, maybe we can enlarge a little bit. Okay, make the rate better. What is the price to pay? The price to pay, the distance may drop. The distance may drop. And then he says, okay, so here is my enlargement theorem. You can check in that reference. Is also widely used in works of people who look into quantum codes. Here you enlarge the rate, but you may pay the price in terms of the distance. And this is additive codes over FQ squared. Now, if you have here is a string A, here is a string B, this is over F to N, this is over F to N. You can write this you can write this in terms of 1 yes? What happened? I will turn A1 here and B1 into V1. How? This, I use the basis 1W. I use this, I look at this as a linear space, as a vector space over this, okay? It's a vector space over this, so now I'm using this. So let's say, whatever I have here, I will choose this to be A1, 1 plus B1 omega. Cool, right? Is this clear? So now, I can write this in terms of that. So I do the same for V2 all the way until Vn. Now, here, this is linear. Here, the code is additive. It's F2 linear. Okay? I hope that's intuitively clear at least. So that's what happened. Now, what happened to that? As F2 vector spaces, these two are isomorphic. How do you explain? Well, these spaces, linear combinations become additive over there. That's it. Okay? Now, what happened to the symplectic inner product? So, if two vectors are orthogonal under the symplectic inner product, what happened when you turn them into this? What will the inner product become? Turns out, the inner product now become trace Hermitian. Is the trace of the Hermitian inner product. Because this code here is additive. Okay? Is that clear enough? So now, the main connection is by symplectic inner product. It is now translated also, can be translated into also into a connection based on trace Hermitian inner product. Fantastic. You have a choice working in the quadratic extension or in the original field. It's just that now the length is double, or you can play in the quantum. Very nice. We have this big map. I hope you see it. So, this is linear code. When you do this transform, it is an additive code. C is symplectic, self-orthogonal, if and only if the image is trace Hermitian, self-orthogonal. Now what happens if on the right side here, it is actually also F4 linear? Then the trace Hermitian is the same as Hermitian. Again, this thing, go into this, it becomes additive. What happens if this happens to be linear? Then the trace inner product is also Hermitian. inner product. The trace Hermitian is Hermitian. So that's why what happened is one of the most common connection. People say, I'm going to build stabilizer code and my classical code ingredients are Hermitian self-orthogonal linear F4 codes. This is actually not the full stabilizer, because stabilizer doesn't require linearity. It only requires additivity. Okay? But of course, it's a lot easier to deal with linear code completely than additive. So what is the benefit? If you don't restrict yourself to linear, if additive is okay, sometimes you get better results. The code is bigger. So, theorem 3, which is the main theorem, can now be expressed as this. So, I have a code C, which is self-orthogonal under the trace Hermitian. That's the size. Then I have this quantum code, and the weight follows the same form as before. Okay? If C is F4 additive and is even, that is, the weight is even for all C, then C is trace Hermitian self-orthogonal. This was the reason why I give that problem 5B. Remember your problem set? 5B was about even code, right? It's over F4, right? It's Hermitian self-orthogonal, right? Yeah, that's the connection. So one quick way of checking whether it's self-orthogonal under trace Hermitian is looking at the weight. If there is something which is odd there, then that means it's out. It's not a good candidate. So, we are winding down now. I'm going to give an overview, a bit of overview of what happened if you go into non-binary. So a good survey is this. It's a bit old survey, but a few pointers of things that you may want to look into. So the generalization from qubit to qubit. Okay, so qubit is 3, and then everything else is basically qubit. Markus Grassel and Martin Roteller they are German, so they have a very specific classification. Q-kit and Q-sept and Q-oct. So in that paper they have that, but for me it's like qubit, qtrit, and qdit. Everything else qdit. Okay, so here some of the highlights of this paper. There is this very beautiful Galois correspondence argument there, and the various bound linear programming, all sort of interesting mathematics there. We have no time to discuss this now. So I want to make one remark about the MDS, quantum MDS. You see a lot of them in the literature, okay? Quantum MDS. Why? If you look at all this nested part comes for free for most codes. Cyclic code, how do you get nestedness part? Because they are ideals, and you know that in ideals, to divide is to contain. If your generator polynomial divide the other generator polynomial, that means that one is contained in you. Nestedness is free. And then all this duality, Euclidean dual, Hermitian dual, you can characterize it using the polynomials. The same thinking happened in the algebraic geometry code. Everything with that same structure, nestedness comes for free, duality you can characterize. One part which is very difficult is the distance. Distance is very difficult. Even things as nice as cyclic code is not settled. Far from being settled. Okay, we have BCH bound, HT bound, so many bounds. They are still far from giving you a very good estimate. I think the same thing also extended to other type of code, DNA code, and all this. The bound issue is difficult. Why so many works in MDS? Because MDS doesn't have problem with the distance. We know completely the weight in the MDS code. In fact, my first paper with Marcus Grassel and Patrick Solé, motivation comes from Marcus. Marcus says, do we really know everything about the weight of MDS? The textbook says, yes, we know. But then we found counterexamples and more counterexamples. And that started making us very nervous. If there are so many counterexamples, then many of these results will be invalid. Luckily, we characterized that there are only 3 counterexamples and they are easy to handle. That was a work in 2011, I think. But MDS, the thing which is interesting for MDS, we know their distances. And therefore, that's a lot of work that is done on MDS so there we don't just say this is the lower bound on the distance. We say that's the distance. So a good recent list is table 5 this is Bo Chong Chen and Ling San. Okay, and this is I think the professor of Bo Chong. So you see table 5, you see a whole lot of parameters of the things that I've done from certain constant cyclic code. But for small fields, Grassel and Roteller has this ISIT 2015 papers where they really present the complete map of what is known. Okay? More work continued to appear, the same route, the same technical underlying ideas, but more complicated analysis. More and more complicated analysis. So what's the problem with MDS? You don't go qubit and qubit in MDS. MDS, the length is bounded by the field size. So if it is binary, if it is quaternary over F4, the best length you can get is 6, length 6. So it is very nice mathematically, very challenging work as well. But in terms of usefulness for quantum error control, as we know it right now, not very much. So here, the need for better bound. Okay. So the determination of the distances, this needs a lot of work. Still, up to now, even for quasi-cyclic constructions, okay, the distance, because we don't usually have very good estimate for the distance, and computing the actual distance using magma can take months. Really not very practical. So more theoretical works need to be done on finding that. And this is what I've learned. Actually, after my PhD, I went for my first postdoc was with the theoretical physics department, and that's where I realized that, you know, this is the most important part that they care about. And so I stopped foolishly doing all this F128 and try to only do works, meaningful works in this small one. That's why I didn't get any good results for many years. Okay, so it's very challenging because a lot of people have been doing work on this, a lot of computations. To beat the one in Grassel table, it's not easy. It's quite difficult. You can produce quantum codes, but then if it is not better than what is already known, what's the point? And here is another one. Some people try to sell it this way. Yes, but I use different classical code, you know. It's the same parameters, but my classical code is different. I hope by now you will know that that argument doesn't work here. We care only about the error operators. So if these 2 different classical ingredients characterize the error the same way, quantum-wise, it's the same. It's not different. So when I'm referring works like that, I will say, yeah, you publish it to some classical work, classical code works. Okay, not in the quantum direction, because that in this world it doesn't have any meaning. Okay, you don't argue that way. Well, my classical ingredient is different. Yes, but the quantum one is the same. Some people even say, here is a classical, okay, the parameter is worse, but you know, the classical code is different, so. Well, as far as we concern in quantum world, it's not that way. So this is my last 2, I think. Okay, right on time. Classically, we have this thing called construction X. I tried my best to present it in a way that is quick and understandable, but I couldn't, because it takes several steps. Okay, so, but the quantum construction X, it was first proposed by Lisonek and Singh, Design Code and Crypto, 2014. And this is connected to what Sujitman taught you about Hull, and what Buket will discuss also tomorrow about LCD code. Okay, so I have linear code C, and then I consider the intersection, so the Hull, the intersection between the code and its dual. If LCD, the intersection is trivial, right? It's just a zero vector. Well, okay, if this intersection is C, that means this is self-orthogonal. That means that's stabilizer. You can use it as a stabilizer. Now, what they are proposing is something interesting. What if you have this, not C, not the whole C, not zero, but something big. It's not C, but maybe, you know, C drop something. One dimension lower. Okay? Or 2 dimension lower. They come up with a method on how to turn this kind of classical code into quantum code. Actually, it's still stabilizer, but using a bit of roundabout way. Okay? So, if you have a structure like this, so this is K. K is the dimension of C, right? K is the dimension of C. So, when this hull is big, this dimension here is maybe K minus 1, K minus 2. Okay? So, that means E here is K minus quantity K minus 1 or K minus 2, it will be 1 or 2. So, when the hull is big, this E is small. If E is small, let's say 1 or 2, you extend the length, okay? You gain something in the dimension, okay? And if there is no drop in the distance, then you may end up with a good quantum code. So, again, if E is 0, this is the case of stabilizer. If E is 1, then maybe the drop in the minimum distance is not so bad. You can still work. So, their proposal in 2014, they use cyclic code. And they found improved qubit. So this was rather big because they proposed a new method, and then they say, hey, using this, you bit the best performing one. So that's how you usually make contribution, okay? You design something or you search, and then it is strictly better than the previous one. If it is the same, then well. So, it is the reason why it's always good to hang out with friends and share your problems. No, mathematical problems, okay, not other problems. So, we were together in Ankara, Patrick Solé, me and Buket, and I mentioned to them, can we use this for quasi-cyclic? Because they are the really expert in quasi-cyclic, and I know only a little bit. So I told them, look, this looks a very promising thing. Can we use this? And I think the two of them discussed with me there, you know, a few minutes, and I think they find a line of attack, and then basically 2 coffee sessions, we know what to do. The search takes longer, of course, and writing the code and designing the hull takes longer. But essentially, we applied that to quasi-cyclic, and yeah, so this is a very new paper. We designed quasi-cyclic code with large hull. We actually use also the self-orthogonal under Hermitian. Okay? So for qubits, we find this code. which is strictly better than the prior best known. I'm not sure if Marcus has updated the table, but before this paper, the best known is this, and we improve 1. Is this a good improvement? Look at the distance. Here with 6, how many errors can it fix? 6 minus 1 over 2 floor. That's 2. Our code can fix 3. So, it's improvement. And then we do propagation. So there are ways of constructing codes by truncating, you know. There are propagation rules. We call it propagation rules. We apply propagation rules. We found this. 3, but they only match the current best. So we say that, well, propagation rule doesn't give you the thing. But look at that. This is a short length relatively, and we still can make contribution. So that says several things. Several things, which is, number 1, the state of the art here is not very high. There's still a lot of work to be done. And progress is relatively slow because determining minimum distance is a lot of work. Now what about in Qthread? In Qthread we even for shorter length we find optimal. What does optimal mean? In the first case, we find a code which is strictly better, but it hasn't reached the upper bound yet. Upper bound is still 1 more actually. But optimal means we improve on the actual construction and it hits the upper bound. So there is nothing better. Certified that there is nothing better. So we have that for the Qthread. Again, this is 2 error correction and the previous one is just 1 error correction. Okay? So that one is 1 error correction, this one is 2 error correction. And we apply propagation rule, we obtain 4 more. Oh, sorry, 3 more. 3 more strictly better and, oh yeah, 4 more. 4 more. So in total we have 6 codes which are better than previous ones. So why not extend to bigger length? Well, when the length is bigger, it takes longer to determine the minimum distance. So a few things that we can do is to make sure we have better bounds. Look into it. Okay, so many things are not discussed. It works. Look, hybrid code. Can we simultaneously transmit quantum and classical? There's a paper by Marcus Krasel and Bei Cheng in 2017 that started says, can we do both? Or can we use the classical code to transfer how it is encoded? So there is this concept called code world stabilize. So it is a generalization of Stin enlargement. Stin enlargement is just by a little. They say what if we add the coset? Keep adding the coset and see how it affects the minimum distance. If the drop is not too much, then maybe we can do it. Asymmetric quantum code, which is actually very close to what I've been doing, but we don't have time to do that. Entanglement assisted. Sompong Chitman has a few work in here. And the decoding issues, implementation in quantum circuits. Toric codes can be expressed in terms of stabilizer actually. At least there is a big intersection as far as I know. So these things we don't discuss. Okay? So it can be an interesting direction if you want to look into. So I'll stop here and entertain questions if you have. Question? Okay then. If not, then okay, thank you. Thank you for your attention.
Okay, thank you for Dr. Frederic Ezerman for the lecture today. And we may invite Dr. Aloysius Suciana to come to stage and hand over the souvenir.